Let's continue on chapter 8, section 2. We're going to talk about area of surface of revolution. Normally you've seen something similar to this when we calculated volume in calculus 1. Here, let's say you want to calculate surface area. So let's start with simple examples that we already know. So if you have a cylinder with radius r and height h, then the surface area around the cylinder would be basically, you can open up the cylinder, and if you cut it through somewhere here and open it up, it's just a rectangle where the height is h and length is basically this parameter of the circle, which is 2 pi r. So the area would be 2 pi r times h. So this is if you're dealing with the cylinder. What if you have a cone with the radius r and the length h? This length L. This length is not orthogonal. This here, the orthogonal would be h, but let's ignore the orthogonal height. Let's say we know the length L. If we know the length L, then simply the area could be, you can cut through this cone and open it up. Then you would have this base would have a radius of r. So the parameter would be basically 2 pi r. So this parameter, which is that this quarter of a circle would, not quarter, a section of a circle would be basically that parameter 2 pi r, the length L, and the angle theta is basically, if you open this cone, you will see the angle. It's not always a fixed angle. It depends on L and radius r. So the area would be basically, area could be calculated through the angle theta multiplied by L, which is basically, you can relate these two and say, okay, the area would be 1/2 L squared theta. This is nothing really new. This is true trigonometry. You should have seen this. The area would be calculated by 1/2 L squared theta, where theta is basically this angle, but theta is kind of related to the radius and L. And so instead of theta is basically the radian, and radian angle would be depending on this length 2 pi r and this length L. So theta and radian would be 2 pi r divided by L. So instead of theta in the equation, you can replace basically 1/2 L squared times 2 pi r divided by L. And this is just the section of the circle. So if you had a circle, you would say the area of a circle would be pi r squared. This, you can look at it as, this is if you're dealing with a circle. It's the same as 1/2 2 pi. This 2 pi is basically the total angle of a circle, which is 2 pi. So if the angle is theta, then it should be 1/2 times theta times r squared. And in this case, r, the length, this radius of the circle is basically L. That's why we have that formula 1/2 L squared theta. Anyway, if you simplify it, the result is pi r L. This is what you have if you're dealing with the area of a cone, surface area of a cone. And we will use this idea to discuss revolution, surface revolution. That's why I started with these. We're going to build on this. So let's say if you have only a section of this cone and not the top part. Let's say we have this highlighted section and they want to calculate the surface area in this part. So what you can do is calculate the bigger surface area minus the top surface area. That's what you can do, and basically after simplification, this is the lower surface area, the whole surface area minus the upper surface area, and that's what you get is the area of this highlighted section. And after simplification, what you notice is that the area would be pi times the top radius plus the lower radius multiplied by this length L. So you can rewrite it actually as, so here, if, I already wrote it here. So if you define a new radius as the average of those two radiuses, if you write R1 plus R2 divided by 2 and call it R, so as the average, then this is nothing but 2R. This would be exactly the same as 2R. So what you have is 2R times pi times L, or 2 pi RL, assuming that the R is the average of those two radiuses. And now this is kind of much easier to remember. And you can compare it to what you have here. If your cone is full, then the upper part of the cone has radius 0. So the average of R plus 0 divided by 2 is basically R half. So when you replace R half into this equation, instead of R, what you get is 2 times pi times R half times L. The 2's will cancel out, and simply you'll get again pi RL. This is if you have the full cone. Okay, so let's remember this formula we will use to discuss the surface area corresponding to revolution. Okay. Let's assume you're given a function, y equal to f of x. And they say rotate this function around the x-axis, and then you will create this, not a cylinder shape, but it's just a circular shape. At any point you would have a circle around the x-axis because you're rotating those points on the curve. So you would have these two, for example, circles going around. And what do you want to calculate if the question is what is the surface area in this rotation from A to B? Then what you can do is, again, like areas when we broke it up to smaller pieces and calculate each one and then approximated it and sum over all those, and we replaced it with integration through limit, then you can do the same thing. So if you consider maybe a section of the graph, maybe this black section, and draw it out here, what you notice is that you kind of have this shape that is very close to that part of this cone without the upper part. And you would have two radiuses. One is the corresponding, this radius is corresponding to the y value at that point, and the other one is correspond to the y value at the point x2. So one is, this would be y1, which is f of x1, and the other height or the radius of the other circle would be y2, which is exactly the same as f at x2. So we can calculate if you remember the area, now the area of the cone would be 2 pi RL, where R is simply this average of the radiuses. This is R. R is the average of the radiuses. That means y1 plus y2 divided by 2, or this is the same as f of x1 plus f of x2 divided by 2. And so I can say instead of R, I can replace it with f of x1 plus f of x2 divided by 2, and if you multiply by 2 pi, then simply you will have pi times f of x1 plus f of x2 multiplied by L. Now the question is, what is this L? Because this is a curve, it's not a straight line. We kind of can approximate this curve again by a straight line, or we can use the length formula that we already found. So this length of this curve, we can figure it out through the from the last section. We can figure out what is the length of the curve, and the length of the curve L is basically the integration is the Sx function, or the integration of this square root of 1 plus f prime x derivative, f prime x squared. And what you have is now, instead of, if you make the length of these, the difference between x1 and x2 smaller and smaller, then what you get is basically f of x1 and f of x2 very close, so you can replace it with basically f at some value x by the intermediate value theorem, or just by an average, expecting that those two are going to be very close to each other. So what you would get is pi times 2 f of x multiplied by L, which L is the length, which is that square root of 1 plus f prime x squared. This is where this formula comes from to calculate the surface area. So the surface area, the final simplified format of surface area, is the integral from a to b of 2 pi times y, or f of x, this could be f of x as well, here f of x, times the square root of 1 plus dy over dx squared dx, or if you write it in terms of function, so multiply by this length function, which is square root of 1 plus f prime x squared dx. This is if we rotate it around the x-axis. If you rotate it around the y-axis, then the lengths, instead of y here, you would have x. This is throughout the rotation about x-axis. If you rotate it around the y-axis, what happens is you would have the same integral. Now instead of y, you would have x multiplied by the 1 plus dy over dx squared dx. The length is still this length, assuming that y is still a function of x, the length is still there. The y changes the x because it's the distance. So if you rotate, let's say if you rotate some curve like this around the x-axis, what you get is these two radiuses that you have to figure out. This radius is simply x1 and the other radius is x2. And they're both depending on x, not dependent on y. So the radiuses are simply x, so they're average x1 plus x2 divided by 2. Which, if you assume that x1 and x2 are very close to each other, this is simply x. 2x divided by 2, or just simply x. So if you have rotation about the x-axis, there is a y there. If you have rotation about the y-axis, you can turn the y into x and still calculate the formula. Yes, so here I already wrote it actually. So if you have rotation, this radius is basically x, 2 pi x square root of 1 plus f prime x. So assuming that we still have a function and not a curve. If you have a curve, then you have to deal with the you have to change the graph and look at through the other view. So let's do a couple examples to make sure that we understand how to use these formulas. It shouldn't be any more that much complicated. It's very easy to follow. So find the area of the surface obtained by rotating this curve from over the interval -2 to 2 about the x-axis. So if I want to find the area would be, the surface area would be the integral from -2 to 2 of 2 pi times y multiplied by square root of 1 plus dy over dx squared and dx. This is exactly the same as here, 2 pi y times 1 plus make sure that you see it. You can use that or you can use the function. But since here they wrote in terms of y, I use that. And if it was written in terms of a function, I would use it in terms of a function. So it would be from -2 to 2, 2 pi times, instead of y, we have square root of 4 minus x squared, multiply by square root of 1 plus, what is the derivative of y? So we just need to figure out what is dy over dx. And if you calculate dy over dx, you would get negative 2x divided by 2 square root of 4 minus x squared. So you can cancel out these two actually. So you get negative x divided by square root of 4 minus x squared. So I'm going to do that. Negative x divided by square root of 4 minus x squared dx. After a bit of simplification, negative 2 to 2, you'd have 2 pi square root of 4 minus x squared multiply by square root of 1 plus, so this term squared would be basically 1 plus x squared divided by 4 minus x squared. And you can do common denominator just to simplify it a bit more. So this is from negative 2 to 2, 2 pi square root of 4 minus x squared multiply by, if we do common denominator, what we get is square root of 4 minus x squared plus x squared, so you would get 4 divided by 4 minus x squared. And now simply, this is under the square root, can cancel out of that term. Square root of 4 becomes 2. 2 times 2 pi, you get 4 pi from negative 2 to 2. And what is that? That is 4 pi is dx here. 4 pi x evaluated from negative 2 to 2, which becomes 8 pi minus negative 8 pi, which becomes 16 pi. So this is finding the surface area obtained by rotating this curve. And by the way, this curve is nothing too complicated. This is just a circle of radius 2, upper half of the circle. So if you rotate it around the x-axis, what you would get is basically a sphere. You get this sphere which has radius 2. So what would be the surface area of the sphere? There's the surface area of a sphere, pi r, 4 pi r squared. Yeah. And since radius is 2, so you'll get basically 4 times pi times 2 squared, which is 16 pi, exactly the same answer. So you can prove that the surface area of a sphere is 4 pi r squared just by going exactly through the same process. As a practice, maybe try to do that. Okay, here's another one. Find the area of a surface resulting from rotating the parabola y equal to x squared about the y-axis. So here, this is from 2 to 2. Okay, so here in this case, we're going to rotate it around the x-axis, sorry, y-axis. So the surface area simply becomes the integral from a to b. Always try to write the steps down before replacing these. So 2 pi times, instead of y, I should replace x because the radius now is x, and multiply by square root of 1 plus f prime, or in this case dy over dx squared dx. And again, we change this y to x just because the rotation is about the y-axis. So when you rotate about the y-axis, if you rotate the curve about the y-axis, what you get is this radius is depending on x, not y. If you rotate it around the x-axis, this radius r is basically the corresponding y value. That's the difference between rotation about the x and y-axis. Okay, so a and b. A is given from 1 and 1 to 2 and 4. We only care about the x values. The boundaries are depending on x. So from 1 to 2, 2 pi, 2 pi times x times square root of 1 plus, we just need to figure out what is dy over dx. dy over dx is simply 2x squared dx. And this is not complicated anymore. 1 to 2, 2 pi x square root of 1 plus 4x squared. And you can pick substitution if you want. Let u equals 1 plus 4x squared. Then du becomes 8x squared dx, 8x dx, and therefore du divided by 8x equals dx. And you can update the boundary. U would be, if x equals to 1, what happens to u? If x equals to 2, what is the u value? If x is 1, so you would get 5 for u. If x is 2, then you have 2 squared times 4, 16, 17. Get the u to be 17. So I can say this surface area is the same as the integral from 5 to 17, 2 pi x times square root of u multiplied by, instead of dx, we have, there should be a dx here. Instead of dx, we have du divided by 8x. And these x's can cancel out. You can cancel out the 8 and 2 and keep a 4 here. So it would be integral from 5 to 17 pi over 4 and u to the power 1/2 d. And if we integrate this, this is at this point it's it is calc 1, simply integration. Add 1 to the power, divide by the same thing, so you would get u to the power 3/2 divided by 3/2, which is 2/3 u to the power 3/2, and evaluate from 5 to 70. And that is pi over 6 multiplied by, if you replace 17, you'll get square root of 17 cubed minus, if you replace 5, square root of 5 cubed, whatever this number is. So this is the area of the surface resulting from that rotation about the y-axis.